All right, welcome back everyone to the deep dive. Today we're diving into a topic that's kind of all around us, even if we don't always think about it. And that is periodic motion. Things moving back and forth, like a swing or even the ocean waves.
Yeah, or even something like a spring bouncing up and down, really common stuff.
Yeah, exactly. But like I said, even though it seems simple, it's actually super important. It's like the basis for understanding all sorts of other things, like waves, sound, even electricity and light.
Yeah, you're totally right. Periodic motion is a real cornerstone. Like it's the foundation of so many other things in physics.
Exactly. So that's what we're going to be exploring in this deep dive, really getting to the bottom of what periodic motion is all about. And we're going to be focusing on two main examples to help us along the way. The spring mass system, a mass bouncing on a spring, and then also the pendulum, the classic swinging pendulum.
Good choices, good choices. Those are the classic examples for a reason.
Right. And we're going to be starting off by breaking down some of the key terms and vocabulary we need to talk about oscillation. Then we'll be diving into a really special type of motion called simple harmonic motion, or SHM.
Ah, yes, SHM.
It's a bit of a mouthful, but trust me, it's pretty awesome.
It is, it is.
So we'll be exploring that, and then we'll look at the energy involved in these motions, some real-world examples of where all of this stuff pops up, even down to the microscopic level.
Oh, yeah, it gets really interesting when you see the parallels in different areas of physics.
It does. And then, of course, we'll talk about pendulums in more detail, and then we'll even get into what happens when those nice, smooth oscillations start to die down, or when they're given a bit of a push from an outside force.
Yeah, the real world is always a little messier than the ideal scenarios we start with.
It is. But we got to start somewhere, right?
Yeah, absolutely.
Okay, so let's get down to the basics. When we talk about oscillation, there are a few key terms we absolutely need to understand.
First one, amplitude.
Amplitude. So picture that spring bouncing up and down. The amplitude is simply how far that mass travels away from its resting point, like the maximum distance from the middle point. And we usually use a capital A to represent amplitude.
And it's always positive.
Always positive. Good point. And we measure it in meters, the standard unit for distance. And just a little tidbit here, for an ideal spring, the total distance it covers in one full bounce, going all the way down and then back up, that's twice the amplitude.
Right, exactly.
Okay, next up, we have a cycle, or sometimes it's called a complete vibration.
A cycle is like one full repetition of the motion. So if our spring starts at the top, it goes all the way down and then back up to the top again, that's one cycle.
One complete back and forth movement.
Yeah, exactly. Back to where it started.
Perfect. Now, how long does it take for one of those cycles to happen? That's where the period comes in. We use a capital T's for this one. And it's simply the time it takes for one cycle to occur, measured in seconds.
So if our spring takes 2 seconds to go down and back up, the period is 2 seconds. Straightforward.
Straightforward. And then we've got frequency.
Frequency is how often those cycles are happening, how many cycles we get per second.
And we usually use a little f for frequency. And it's the inverse of the period.
Meaning F equals 1 divided by T, 1 over T.
So if the period is 2 seconds, like in our example, the frequency would be 1 cycle every 2 seconds, or 0.5 cycles per second. And the unit we use for frequency is hertz, shortened to hertz.
Hertz. So 1 hertz just means 1 cycle happening per second.
Easy. Okay, and the last key term we need is angular frequency. And this one might seem a bit more, I don't know, maybe a little intimidating at first, but it's really useful.
Oh yeah, angular frequency is a super helpful concept, especially when we start thinking about things like rotational motion later on.
For sure. So we use the Greek letter omega for angular frequency. It looks a bit like a curly W, but for simplicity, let's just call it V.
Sounds good.
And it's related to regular frequency. And the period by the equation, V equals 2 pi times F, which is also equal to 2 pi divided by T. The unit for angular frequency is radians per second.
Now, what's really fascinating here is that for any of this oscillation to even happen, you absolutely need a restoring force.
Oh, the restoring force, right.
Yeah, think about that mass on the spring again. When you pull it down, the spring wants to pull it back up to its resting point. That pull, that's the restoring force.
So it's the force that always wants to bring things back to the middle, back to equilibrium.
Exactly. And the further you pull the mass away, the stronger that restoring force usually gets. And because of Newton's second law, which tells us force equals mass times acceleration, that restoring force leads to acceleration, and that acceleration is also directed back towards the equilibrium point.
Right, so it's like the force is always trying to pull it back to the middle, and that causes it to accelerate in that direction.
But here's the thing. Because the mass has inertia, it doesn't just stop nicely at the equilibrium point. It overshoots, and then the restoring force kicks in again, pulling it back the other way.
Oh, I see. So it's that interplay between the restoring force and the inertia of the mass that creates that back and forth motion.
Precisely. It's like a constant tug of war between wanting to be at rest and wanting to keep moving.
It's like a dance, a constant dance around the equilibrium point.
Exactly.
Okay, so now you mentioned before this special type of oscillation called simple harmonic motion, SHM. What makes that one so special and so, I guess, simple?
So in SHM, what sets it apart is that the restoring force is directly proportional to the displacement from that equilibrium position.
Directly proportional, meaning?
Meaning, if you double the displacement, you double the restoring force. A nice, clean, linear relationship.
Ah, so if you pull the spring twice as far down, it pulls back twice as hard.
Precisely. And a perfect example of this is our ideal spring. The force it exerts is actually described by Hooke's law, which is F subscript x equals negative kx. F subscript x being the restoring force. X is the displacement from equilibrium, and k is what we call the force constant of the spring, basically a measure of how stiff it is.
Oh, so like some strings are really easy to stretch. Those would have a low K. But other springs, you can barely move them. They're really stiff. Those would have a high K.
Exactly, and that negative sign in Hooke's law, that's super important. It tells us that the force is always acting in the opposite direction to the displacement, always trying to restore it back to equilibrium.
Got it. So the force is always pushing or pulling it back to the middle.
And because we know force equals mass times acceleration, the acceleration in SHM, it's also proportional to the displacement, but in the opposite direction. The equation is a subscript x equals negative k over m times s.
Okay, I'm following so far. Now, you mentioned earlier this really interesting link between SHM and uniform circular motion.
Yeah, a lot of people find that connection really surprising, but it's super elegant and really insightful.
It does seem kind of unexpected.
Yeah.
How can something going in a circle be related to something bouncing back and forth in a straight line?
So imagine an object moving in a perfect circle at a constant speed. Now, if you were to shine a light from the side onto that object, its shadow would be projected onto a wall, right?
Yeah.
Well, that shadow, it would be moving back and forth along a straight line, and that motion would actually be simple harmonic motion. We can represent this circular motion with a rotating vector, which we call a phasor. And the projection of that phasor, if you imagine shining a light on it and looking at its shadow, that projection onto the diameter of the circle, that exactly matches the displacement of an object undergoing SHM.
Oh, wow. That's a really cool way to visualize it. So it's like if you just focus on one component of that circular motion, like the up and down and the side-to-side part,
Yeah.
it looks and behaves just like SHM.
Precisely. And this link helps us understand the angular frequency of SHM in a new light. Remember, we called it V. And in SHM, this angular frequency is actually determined by the physical properties of the system, specifically the mass m of the object that's oscillating and the force constant k of that restoring force.
Okay.
The relationship is V equals the square root of k divided by m. It's a fundamental property of the system.
So if you have a stiffer spring, a higher K, that means a higher angular frequency, meaning it oscillates faster. And if you have a heavier mass, the larger M, that slows things down, lower angular frequency, slower oscillations. Makes sense. A stronger spring wants to snap back quicker,
Yeah.
and a heavier object is just harder to get moving.
Exactly. And from that angular frequency, we can get the regular frequency f and the period t. The equations are frequency f equals v divided by 2 pi and period t equals 1 divided by f, which is also equal to 2 pi divided by v.
Okay, so we can basically go back and forth between these different ways of describing the oscillation.
And now here's something that a lot of people find really surprising. The equations for frequency and period, they don't depend on the amplitude of the oscillation at all.
Wait a minute. Are you saying it doesn't matter how far you pull that spring down? It'll still take the same amount of time to go back and forth?
For an ideal system, yes. As long as we're dealing with ideal SHM, the time it takes for one cycle, the period, only depends on the mass and the spring constant, not how far you stretch or compress the spring initially.
It's so weird. It feels like it should take longer to go back and forth if you pull it further.
It's definitely counterintuitive, but it's one of the remarkable characteristics of SHM. In the real world, of course, if you stretch a spring too much, you might start to see it behave differently, and this independence from amplitude might break down. But for the ideal case, it holds true.
Okay, that's a really important point to keep in mind. Now, how do we actually describe where the object is in its oscillation at any given moment?
We can describe the position of the object as a function of time using a trigonometric function, specifically a cosine function. The equation is x of t equals a times cosine of vt plus phi.
Okay, break that down for me.
So x of t is the displacement of the object at any time t. A is our good old amplitude, the maximum displacement. V is the angular frequency we talked about before, that natural rhythm of the system. And then we have phi, which is the phase angle or initial phase.
The phase angle, what's that about?
It basically tells us where the object is in its cycle at the very beginning at time t equals 0. Like, is it starting at the maximum displacement, passing through equilibrium, or somewhere in between?
Oh, so it's like an offset. It lets us adjust the equation to match the actual starting conditions of the oscillation.
Exactly. And the initial position, x subscript 0, is just a times the cosine of phi.
Got it. And what about the velocity and acceleration? How do we find those?
We can use a bit of calculus to figure those out. The velocity subscript x of t is the derivative of the displacement with respect to time, and that gives us v subscript x of t equals negative va times sine of v plus phi, and the acceleration a subscript x of t is the derivative of the velocity with respect to time.
Calculus, oh boy.
Don't worry, the important thing is to see how these equations are related to each other. So the acceleration equation ends up being a subscript x of t equals negative v squared times a times cosine of v plus phi.
Okay.
Now, if you remember, x of t is a times cosine of v plus phi, so we can actually rewrite the acceleration equation as a subscript x of t equals negative v squared times x of t. And if we remember that v squared equals k over mem, we get a subscript x of t equals negative k over mem times x of t, which is actually just what we got from Hooke's law and Newton's second law before.
Ah, so it all ties together. The math works out beautifully.
It does. It's all consistent. And it shows us that the acceleration is always proportional to the displacement, but in the opposite direction. That's that restoring force pulling it back to equilibrium.
Right. So what about the maximum values for speed and acceleration during SHM? How do we find those?
So the maximum speed off subscript max happens when the object is passing through the equilibrium position. That's when the sine function in the velocity equation is at its maximum value of 1. So of subscript max equals a times a. Similarly, the maximum magnitude of acceleration, a subscript max, happens at the points of maximum displacement, where the cosine function in the acceleration equation is at its maximum value of 1. So a subscript max equals v squared times a.
Makes sense. Now, how do these maximum values relate to the position of the object in its oscillation?
It's an elegant back and forth. When the object is at the equilibrium position, x equals 0, the restoring force is 0, so the acceleration is also 0. But that's where the object is moving the fastest. Its speed is at its maximum. On the other hand, when the object is at its maximum displacement, x equals plus or minus a, it momentarily stops before changing direction. So at those points, the speed is 0, but the restoring force is at its maximum, pulling it back towards equilibrium, so the acceleration is also at its maximum magnitude.
Okay, so it's like a trade-off. When the speed is high, acceleration is low, and vice versa.
Exactly. And that makes sense because the acceleration is always trying to change the object's speed, either speeding it up or slowing it down.
Got it. Okay, let's shift gears a bit and talk about energy. What about the energy involved in simple harmonic motion?
Okay, so for an ideal SHM system where we assume there's no friction or any other energy losses, the total mechanical energy of the system remains constant. It doesn't change.
Constant, even though the object is moving back and forth.
Yes, what's happening is that the energy is constantly transforming between two forms: kinetic energy and potential energy. Kinetic energy is the energy of motion, and potential energy is the energy stored in the spring due to its deformation.
Okay.
So the equation for kinetic energy is K equals 1/2 mv subscript x squared, where m is the mass and v subscript x is the velocity. And the equation for potential energy is U equals 1/2 kx squared, where k is the spring constant and x is the displacement.
So as the mass is moving towards the equilibrium point, it's speeding up, so its kinetic energy is increasing. But at the same time, the spring is getting less stretched or compressed, so its potential energy is decreasing. And then, as the mass moves away from equilibrium and slows down, the potential energy in the spring increases while the kinetic energy decreases.
Precisely. It's a constant give and take between these two forms of energy, and the total mechanical energy, E, is just the sum of the kinetic and potential energies. E equals K plus U, which is equal to 1/2 mv subscript x squared plus 1/2 k squared, and this total energy, it stays constant throughout the whole oscillation.
Wow, so it's like a perfect energy exchange.
It is, and we can even express this total energy in terms of the amplitude of the oscillation. Remember, at the maximum displacement x equals plus or minus a, the velocity is 0. So all the energy is stored as potential energy in the spring. E equals 1/2 ka squared.
Right. And at the equilibrium position, the opposite is true.
Exactly. At x equals 0, the potential energy in the spring is 0, and all the energy is kinetic. E equals 1/2 mv subscript max squared. And if you substitute v subscript max equals va and v squared equals k over m into that equation, you'll see that it simplifies to 1/2 k squared, showing that energy is indeed conserved.
That's a nice confirmation. So the total energy is directly proportional to the square of the amplitude.
Yeah.
If you double the amplitude, you quadruple the energy.
Precisely. And we can use this energy conservation principle to actually find the speed of the object to any given point in its oscillation. If we set the total energy E equal to 1/2 ka squared, which is the total energy at maximum displacement, and we set that equal to the sum of the kinetic and potential energies at any other point, 1/2 mvx subscript x squared plus 1/2 kx squared, we can rearrange that equation and solve for v subscript x. And we get v subscript x equals plus or minus the square root of k over m times the quantity a squared minus x squared. Or we can write it using the angular frequency. V subscript x equals plus or minus v times the square root of a squared minus x squared. The plus or minus sign just means that the object could be moving in either direction at that point.
Okay, I think I'm starting to get a good handle on the energy side of SHM. Now, we've been talking a lot about the spring mass system, but you mentioned that SHM can apply to other systems as well.
Absolutely. Remember, the key ingredient for SHM is that restoring force that's directly proportional to the displacement from equilibrium. So any system that exhibits that kind of behavior can be described using the principles of SHM.
All right, so give me some examples of where else we might see SHM in action.
Okay, so let's imagine a mass hanging from a vertical spring, like maybe a weight on a spring scale. Now, gravity's pulling down on that mass, right?
Yeah.
But what gravity really does is just shift the equilibrium position downwards a bit. The spring stretches a bit more to balance the weight of the mass. But if you then displace the mass from this new equilibrium position, it will still oscillate up and down in SHM.
Oh, I see. So gravity just changes the resting point, but the basic oscillations are still the same.
Exactly. And importantly, the angular frequency, Ves, equals the square root of k over m. It remains the same whether the spring is horizontal or vertical. Gravity just affects where that equilibrium point is.
Interesting. So it's like gravity just sets the stage, but the SHM is still the star of the show.
Precisely. Now, what about rotational motion? Can we have SHM in systems that rotate or twist?
That's a good question. I guess it would have to be some kind of back and forth twisting motion.
You got it. And that's exactly what we call angular SHM. This occurs when a system experiences a restoring torque that's proportional to its angular displacement from its equilibrium orientation.
Okay, torque. Reminder, what's torque again?
Torque is basically a twisting force. Like when you use a wrench to tighten a bolt, you're applying a torque.
Right, got it.
So in angular SHM, the equation for the restoring torque is tau subscript z equals negative kappa times theta, where tau subscript z is the restoring torque, theta is the angular displacement measured in radians, and kappa is the torsion constant.
Torsion constant. That sounds like the rotational equivalent of the spring constant.
Precisely. The torsion constant tells us how much torque is needed to twist the system by a certain angle. A higher torsion constant means it's harder to twist.
Okay, so a stiff spring has a high K, and a system that's hard to twist has a high kappa.
Exactly. And the angular frequency for angular SHM is V equals the square root of kappa divided by I, where I is the moment of inertia of the object.
Moment of inertia. That's another one of those physics terms that can be a bit tricky.
Yeah, the moment of inertia is basically a measure of an object's resistance to rotational motion. It depends on the mass of the object and how that mass is distributed around the axis of rotation.
Got it. So a heavier object, or an object with its mass further away from the axis, will have a higher moment of inertia, meaning it's harder to get it spinning.
Precisely. And the period for angular SHM is t equals 2 pi times the square root of I divided by kappa. Now, a classic example of angular SHM is the balance wheel in a mechanical watch. You know those tiny wheels that oscillate back and forth?
Yeah, I've seen those.
Well, they're connected to a tiny hairspring, and as the wheel rotates, it twists and untwists that spring. And that spring provides a restoring torque that's proportional to the angle of twist, leading to really precise angular SHM, which is what helps the watch keep accurate time.
Wow, that's pretty amazing. So that little tiny wheel in a watch is basically a tiny example of angular SHM.
Exactly. It's a beautiful example of how these principles show up in unexpected places.
It is. And speaking of unexpected places, you mentioned before that SHM even shows up at the microscopic level.
It does. Think about the atoms within a molecule. They're constantly vibrating relative to each other, kind of like tiny masses connected by little springs. And for small vibrations, the forces between those atoms, the forces that hold the molecule together, they can be really well approximated as being proportional to the displacement.
Oh, I see. So those tiny vibrations, they're like miniature examples of SHM.
Precisely. And that means we can actually use the same mathematical tools to describe those molecular vibrations. The effective spring constant, the K in this case, depends on the strength of the chemical bonds and the shape of the energy landscape of the molecule.
Wow. So we can apply the same principles we've been talking about to understand how molecules vibrate. That's pretty mind-blowing.
It is, and this understanding is actually incredibly important in fields like spectroscopy, where scientists analyze the frequencies at which molecules vibrate to learn about their structure and how they interact with light.
Fascinating. So from big things like springs and pendulums to really tiny things like molecules, SHM is everywhere.
It's a fundamental pattern in nature.
Okay, let's move on to another classic oscillating system, the pendulum. Let's start with the simple pendulum. What makes it so simple?
The simple pendulum is a really idealized model. We picture it as a point mass, which we call the bob, hanging from a massless, unstretchable string, and it's free to swing back and forth under the influence of gravity.
Okay, so in the real world, you can't have a point mass or a massless string.
You can't. But it's a good approximation for a lot of real pendulums where the bob's mass is much larger than the string's mass, and the size of the bob is small compared to the length of the string.
So like a pendulum in a grandfather clock would be a pretty good real-world example of a simple pendulum.
Exactly. Now, when you pull the bob away from its resting position, hanging straight down, gravity acts on it, trying to pull it back towards the middle. And for small angular displacements, the restoring torque that gravity provides, it's proportional to the angle.
Okay, angular displacement. That's the angle that the pendulum swings away from its resting position, right?
Yes, and we usually measure it in radians.
Now,
So the equation for the restoring torque is tau equals negative mgl times theta, where m is the mass of the bob, g is the acceleration due to gravity, L is the length of the pendulum, and theta is that angular displacement.
that equation looks a lot like the one we saw for angular SHM earlier.
Hmm.
Tau subscript z equals negative kappa times theta.
Good observation.
Oh,
And because the restoring torque is proportional to the angular displacement for small angles, the motion of a simple pendulum is actually very close to being simple harmonic motion. The angular frequency for a simple pendulum is v equals the square root of g divided by L, and the period, the time for one complete swing, is t equals 2 pi times the square root of L divided by g.
and here's the really surprising part again. The mass of the bob. It completely disappears from those equations.
It does. So for a simple pendulum, the period of the swing only depends on the length of the pendulum and the acceleration due to gravity. Doesn't matter if the bob is heavy or light, if the length is the same, the period will be almost the same, at least for small swings.
So a heavier pendulum and a lighter pendulum of the same length, they'll swing at basically the same rate.
They will. But it's really important to remember that this approximation, this idea that the pendulum behaves like SHM, it only works for small angles. If you swing the pendulum really high, the motion gets more complicated, and the period starts to depend on the amplitude as well.
So for those grandfather clocks with big, wide swings, the period isn't perfectly constant.
That's right. It's only approximately constant for those smaller swings.
Okay, good to know. Now let's get a little more realistic and talk about what's called a physical pendulum. What's a physical pendulum?
A physical pendulum is basically any real pendulum where the mass isn't just concentrated at a single point, but is distributed over some extended object.
So instead of a point mass on a string, it's like a baseball bat swing from a pivot point, or even the whole pendulum rod in a grandfather clock.
Exactly. And the period of oscillation for a physical pendulum is a bit more complicated to calculate. It's t equals 2 pi times the square root of I divided by mv/80. I is the moment of inertia of the object about the pivot point. M is the total mass of the object. G is still the acceleration due to gravity. And D is the distance from the pivot point to the center of gravity of the object.
That equation looks a bit tougher than the one for the simple pendulum.
It is, but it's more general. It takes into account the shape and mass distribution of the pendulum. But check this out. If we imagine that all the mass of the physical pendulum were concentrated at a single point at distance L from the pivot, just like in our simple pendulum, then the moment of inertia I would be ml squared, and the distance to the center of gravity d would also be L. And if you plug those values into the physical pendulum equation, it actually simplifies down to the simple pendulum equation.
Oh, that's neat. So the simple pendulum is just a special case of the physical pendulum.
It is, and this concept of the physical pendulum, it's actually used by biomechanists to study how animals walk and run.
Really?
Yeah, they can model the swinging motion of an animal's leg as a physical pendulum. By knowing the moment of inertia of the leg and where its center of gravity is, they can figure out the natural frequency of the leg swing and analyze the animal's gait and how much energy it uses to move.
That's pretty cool. So these physics principles have real-world applications in biology, too.
They do.
Okay, so we've been talking about these ideal oscillations that could, in theory, go on forever.
Mm.
But in the real world, that's not what happens. Things eventually slow down and stop. Why is that?
That's because of damping.
Damping.
Yeah, in the real world, there are always forces that oppose motion, like friction. It could be friction from air resistance or even internal friction within the object itself. And these forces do negative work on the system, which means they take energy away from it. So the mechanical energy of the oscillating system decreases over time, and that causes the amplitude of the oscillations to get smaller and smaller until they eventually stop.
So that's why a pendulum eventually stops swinging and a spring stops bouncing.
Exactly. And we often model this damping force with an equation that looks like this. F subscript x equals negative BV subscript x. B is called the damping constant, and it tells us how strong the damping force is. A bigger B means a stronger damping force for a given velocity. And the negative sign just means that the damping force always acts in the opposite direction to the velocity, always trying to slow it down.
Okay, so the damping force is always trying to put the brakes on the motion.
Exactly. And the rate at which the mechanical energy of the system decreases due to this damping force is given by dE over dt equals negative BV subscript x squared.
Now, you mentioned earlier that there are different types of damped oscillations depending on the strength of the damping.
Right. So we usually classify damped oscillations into three categories: underdamped, critically damped, and overdamped.
Okay, let's start with underdamped. What does that look like?
Underdamped oscillations happen when the damping is relatively weak. In this case, the system still oscillates back and forth, but the amplitude of those oscillations decreases over time, gradually getting smaller and smaller until it eventually comes to a stop.
So it's like a gradual fade out. It's still oscillating, but each cycle is a little smaller than the one before.
Exactly. And the angular frequency of these underdamped oscillations is actually slightly lower than the natural frequency of the system without damping.
Okay.
And the equation for this new angular frequency, we usually call it V prime, is E prime equals the square root of the quantity K over mem minus B over 2m all squared.
Okay, so the damping affects the frequency a bit.
It does. Now let's move on to critically damped oscillations. This is kind of a special case.
Special in what way?
Well, in critically damped oscillations, the damping is just strong enough that the system returns to its equilibrium position as quickly as possible without oscillating at all.
Oh, so just go straight back to its resting point without any bouncing back and forth.
Exactly. It's the fastest way to get back to equilibrium without any overshoot.
That sounds pretty useful.
It is. And finally, we have overdamped oscillations.
Overdamped, so that's even stronger damping.
Yes, in overdamped oscillations, the damping is even stronger than in the critically damped case. The system still returns to equilibrium without oscillating, but it takes longer to do so. It's like trying to move through thick mud.
Ah, so it's like a really slow, sluggish return to equilibrium.
Exactly. Now, all three of these types of damping show up in real-world applications.
Okay, give me an example.
A great example is the shock absorbers in a car's suspension system. They're designed to provide damping that's really close to critical damping. When you hit a bump in the road, you want the car to quickly return to its normal position without bouncing up and down.
Yeah, I definitely wouldn't want my car to keep bouncing after every bump.
Right.